Hello and welcome. I'm going to be presenting on our project, which is detecting fungal diseases in trees. My name is Nhlanhla, and my partner Lindo and I worked on this project for the MIT808 capstone project. A bit of background on our project. The forestry sector plays a vital role in the South African economy. However, the industry is severely threatened by pests and pathogens. Now, what are pathogens, you may wonder? So pathogens are organisms or agents that can cause disease. So for example, in this case, fungi. Organizations like the TPCP and EPI are studying fungal pathogens to see how they affect trees like eucalyptus within plantation forestry. However, in order to do this, they need to be able to quantify the pathogenicity of fungal strains. And pathogenicity simply means the strength of the pathogen. So the challenges for this project. The primary challenge is that typically fungal pathogenicity is quantified by manually measuring lesions. This process is time intensive, it's labor intensive, and is very error prone. So the solution that we found was to address this using tools like computer vision and machine learning. However, the second challenge that we faced is that for this project there was a significant lack of real and labeled fungal lesion images. So what does this mean for the aim and the objectives of this project? Well, the aim of this project was to utilize these technologies, computer vision and machine learning, to analyze the images and automatically detect and measure the fungal lesions. And we aimed to accomplish this using three objectives. So the first was description. So this would include exploring and characterizing the real image datasets in order to inform data augmentation. And that's the second objective, which is to create synthetic images to augment the real datasets and produce labeled data. Then finally, in the third objective, we would then validate the synthetic images. So we would do this using a convolutional neural network model to detect the lesions and to see, using model performance to test whether the synthetic images actually affected model performance. And we also performed direct dataset comparisons. We then moved on to extracting the parameters, and these are parameters that we'd use to inform augmentation in the following phase. So for this, we looked at color profiles and we looked at structural compositions. So for color profiles, we looked at color clustered images. So we created color clustered images. We also plotted color distributions. And then for the structural compositions, we looked at the structural similarity indexes and then plotted that as heat maps. And we also created average images, which allowed us to look at the sizes of different components in the images, the shapes, etc. And from this, we extracted parameters such as the size, the shape, the color, and the position of all of the different components in each image. We then used that to augment the data. So we actually generated synthetic images. And we created a pipeline that's very easy to use and does this in 3 steps. In the first step, the user sets the output folders and the number of synthetic images to be generated. Next, the script will then use the predefined functions to generate a metadata file with 1 row per image. And then finally, the script will use that metadata file as a guide to generate more synthetic images. So how did we then validate the images in the third and final phase? So we did this in 2 ways. The first was using model performance, and the second was using structural similarity. So for model performance, the idea behind this was that if we can prove that the addition of synthetic images actually enhance the performance of the models, then the synthetic images would be valid. So in order to do this, the synthetic images for each dataset were tested using 6 different CNN models. 3 were untrained ResNet 18 models, the first being trained with real data only, second being trained with synthetic images only, and the third being a dual model. And then we follow the same process for a pre-trained ResNet 18 model. So that brings us up to 6 models for each data set. We then looked at structural similarity, and the idea behind this is that if the synthetic images and the real images are structurally very similar, that means that the synthetic images are more valid and are of more use in the modeling process. So for this, the structural similarity indexes were calculated to compare the real and the synthetic data sets. We then visualized metrics from all of these. So for structure, we use the SSIM values, so the structural similarity index values, and we visualized heat maps. And for modeling, we looked at the loss and accuracy values during training. And then during the testing phase, we looked at confusion matrices, we looked at rock curves in the area under the curve, and we looked at accuracy and F1 scores, which is a measure of reliability. So these are the results we got, and I'm going to do it first in terms of STEM and then in terms of the twig data sets. So for the STEM results, for the untrained models, we saw that there was a significant increase from the real model, so the light green, to the dual model, the dark green, for accuracy and precision. However, recall remained the same, but for F1 score, it also increased slightly. So these are promising results. And then when we looked at the area under the curve, as you can see by the value in the bottom right corner of each of these, Model 1 is the real trained data and Model 3 is the dual trained data. And as we can see, the area under the curve is the same, so these aren't great results, but they're also not bad results. So based off of this, we can see that these models are, somewhat effective. However, we did see a significant improvement from the real trained models to the dual trained models when we did it with a pre-trained ResNet models. So you can see that for accuracy, precision, and F1 score, we have significant improvements. For recall, it goes slightly down. But when we look at the area under the curve, we also have a significant improvement from Model 4, which is trained on real data only, to Model 6, which is trained on a combination of real and synthetic data. So that goes from 54 to 89. So that's quite an improvement. We also then looked at structural similarity for the STEM data set, and these are the results we got. So on the y-axis, we have all of the real images, and on the x-axis, we've got all of the synthetic images. Anything in green or in a lighter color is structurally similar, but anything in brown is an outlier. It means that it's less structurally similar. So as we can see here and here as well, we do have some outliers. But thankfully, we were able to use this heat map to detect these outliers before modeling and remove them so they didn't affect modeling. And as we can see, in general, the structural similarity is quite high, which is a promising result. So in conclusion, for the STEM dataset, both the modeling and the structural similarity results indicate that the synthetic images that were generated are valid. For future work, what can be done is we could use a combined dataset for further model training. So instead of using a phased approach in which we train the dual model using real and then synthetic, or synthetic and then real, we combine the real and synthetic images into one dataset. So that's a possibility. We could also enhance the simplistic synthetic images using methods such as stable diffusion to make them more realistic, and that might increase model performance. Moving on to the twig dataset, the results that we got were very promising. So for the untrained models, we can see a significant increase in accuracy, precision, and F1 score remains the same, even though recall does decrease. However, for the rock curve, we can also see performance increases from 57 to 85, so that is quite promising. For the pre-trained models, we also got good results, and as we can see, the differences are quite significant on this one. And again, for the rock curve, we go from 69 to 84. So that is also a significant improvement. We then also looked at a structural similarity for the twig dataset, and unfortunately we have less structural similarity for the twig datasets when comparing the real and the synthetic datasets. So that's not as promising. So in conclusion, for the twig dataset, what we can see is that while the modeling results indicate that the twig synthetic images are valid, the structural similarity results indicate that they can still be improved upon. So for here, future work could include significantly increasing the size of the synthetic dataset, because, as mentioned, it was only a synthetic dataset of 40 images. And secondly, we can also focus more on the image category with no bark in order to reduce image complexity, as that might be confusing the model. So in conclusion for the project, looking at our contributions, the first contribution is that we have synthetic image generation pipelines for both the STEM and the twig datasets. We also have augmented both datasets, and we have used methods and created baselines for validating those generated synthetic images. And finally, we have CNN models that can detect lesions on the stems and the twigs of forest trees, and these have been proven effective, more effective than simply using the real images. In terms of the limitations of this project, the first would be that the lack of usable size references in the real images means that lesion measurement was not yet possible. So this project focused on lesion detection rather than lesion measurement. And the second one was that due to time constraints, the use of stable diffusion to enhance the synthetic images to become realistic images was not possible either. So future work can focus on both of these. It can focus on synthetic image enhancement and models for lesion measurements. So yeah, that's it from us. Thank you so much.